How's it going, everyone? I'm gonna wait, I would say another 5 minutes before we get started, and then we'll actually go ahead and continue with whatever we were going to be doing. Just because there's not that many people here yet, so. Mhm. Let's see. I'll be putting this online as well. Let me just open. We're gonna get started in just a second. I'm just trying to find her lecture material that she's given so far, so I know what you have covered and what you haven't covered. It looks like you guys are covering graphs right now, which are personally my favorite thing. I don't know if you are covering graphs up to this point, so let's actually use that as our first poll. We'll start by sharing, and this will be recorded and put on YouTube. So if you haven't found it yet, you can find all of these future videos. They're going to get all posted to my YouTube channel. If you haven't found my YouTube channel, you could do so. It should be in the link that I sent out with my, I guess you could say, my email greeting um, through my website. So if you have found it, then perfect. I haven't posted any links. I will post a link as soon as I um, what's it called, as soon as I send out another announcement, just directly to it. But anyways, let's get started. So if we just kind of take a look at what she has for all of you, let's see. I'm going to start a poll. And this poll is essentially going to be, well, I guess, what topic is she now that makes the least sense? Okay, and let's just record names and launch that. So it looks like she's going over searching algorithms. I know that's probably, I'm guessing, last week's content. And I could make an entire video. I was going to make an entire video for you guys regardless, just because I know we missed last week. But just for this week, it's kind of like the topics that she's covering that don't really add up necessarily. I know she has some difficulty communicating some of the graphing algorithms just because there's a lot going on there. Let's see. Okay, sweet. I love graphs. Graphs are my favorite part about this class just because of how cool they are. Hold on, where is it? Where's the notes? Okay. Sweet. Okay. Obviously, if you have been going to her class, then you've probably seen graphs before. If not, you've definitely seen graphs before. Graphs are everywhere. And what they do is serve as kind of like this non-linear data structure that lets us kind of represent information in a relative manner. So really what I mean by that is I could relate objects together by creating connections. And you might be asking, well, what kind of relations can you have on a graph? What could this be in terms of a graph, right? Well, this type of graph can be many sorts of things. Graph. I can't spell, but anyways, this type of graph can be many sorts of things. And you could think of this as kind of like your position in cells. So position I, this could be like north, this could be east, this could be south, and this could be west, right? And you might even have more connections. You might even have, let me redraw that one. This might be northeast. Maybe you have another one over here. No, this would be southeast. And then a southwest. And then northwest. And essentially what you're doing is you're taking some abstract place in your graph and relating it by other adjacent cells, right? So a good example of a graph that I think is kind of useful are grids. I'm gonna pop all of these off just to start with, and I'm gonna kind of scroll down and just kind of go along with the grid idea. So if I create a grid, and then kind of relate this to what we were just talking about, right? We have some center of our grid, right? Maybe this is where our current position is on the graph. You could draw these links between other pieces of this graph and then use this in order to do some interesting things. And maybe you're asking, well, what kind of interesting things can you do? Well, let's start by just kind of discussing, well, how do you actually represent something like this? Well, like how are you representing a graph? And my favorite way to do it is kind of with some sort of graph data structure. So I'm just going to call it G. And one way you could do this is with a list, right? You could have a list of nodes. And each node is going to be, how do you say? Each node is going to be a unique object, and they're all going to have references to each other. So anytime I create a node, I'm going to add it into my list. So we could add, we could subtract nodes, and we could relate nodes. So we could relate node 1 to node 2. Essentially, create a connection. And we could, I guess you could say, unrelate nodes too. That's also possible. But for right now, we're just going to talk about these three things because these are kind of the most important. And also our list representation. So just kind of having some way to store all of our nodes and keep them as kind of like a reference, right? Because when you think of a graph, it's nice to understand that there's all sorts of, I guess you could say, information stored inside of it, but that information has to stem from somewhere, right? So if I had no way to actually stem that representation, then like I can't really do anything with my graph. So one way that I usually store these nodes is in a list. There's other ways too, as well as like kind of like more, I guess you could say, I guess so. If I was to do something like this, I would probably storing a lot of information on these nodes, right? That's one thing that I would keep in mind. Say you're simply, um, say you're simply just keeping track of like one value. Maybe you have like a list of that value. So a list of the value. So list of just some value. Okay. Value. This is like method 2. Whatever the value is, it could be like int, maybe like a char pointer, string, whatever it is. So in this case, we're storing nodes. These nodes represent this information that's being stored on each individual one. And this representation, right? We have all of these values, but now we actually need a matrix. So this matrix is going to serve as our relations. And what you're going to see is right, this matrix is going to be as long. It's going to be a square matrix, essentially. So the number of nodes, I'm going to call those vertices. So this is the number of vertices in our list. It's the same as here, right? So the number of entries, the number of rows in columns is going to be V. So this becomes a V squared matrix. And you could think of this as like, well, if this is V0, does V0 have a connection to itself? I'm just going to leave that as a question mark. Does V0 have a connection to this one? So V1, V1, V2, V3, all the way to Vn. V0, V0, V1, V2, all the way up to Vn. This kind of representation, if you don't have a fully connected, I guess you could say, representation, and maybe you're just kind of having few relationships between your nodes, right? Because this matrix is relating these nodes together. That's important to remember. You're going to have a lot of empty spaces, right? You're going to have a lot of these zeros. So if you have way more nodes than connections, you're going to find that this matrix is very sparse, meaning that we're using a lot of data here, right? You're using V squared. So if V becomes very large, if V becomes larger than E, so you're kind of wasting data. In fact, for every edge, you're going to have 2 entries in here. So if there's V squared edges, you're using 2E. So this is, I guess you could say this is the max That's the max number of edges. And you could see it as if you're going to have at most 2e entries in V. So essentially, unless every single node is connected to every other single node, there's obviously going to be space that you're missing, right? And what I mean by that is, like in this kind of graph here, right? You could see that this is not connected to this node. But I'm going to draw this in red. This red node is connected to these nodes and other nodes in that case. So depending on how big your grid, depending on how big your graph, you're going to have a lot of empty space in this matrix. It's kind of intuitive. I mean, we could kind of work through this math more, but I don't really think it's that necessary. And only because, you know, you could kind of see, right? If I start filling in like maybe V1, right, isn't connected back, maybe it's connected back. It's not connected to itself. It's not connected. It is connected, right? You have all of these zeros, and you could do this all the way down and until here. Maybe you have all zeros here. Maybe all of your nodes are independent. And in that case, you're using a lot of space just to keep track of all of these. Now, there are cases where using a matrix is very useful. Personally, I don't think I've ever really came across one. I will say this though, in smaller applications, so applications almost like this, but more where your values, your list to represent, is small. So you have a small number of nodes. Using a matrix is actually not a bad idea. And also, if time complexity is your utmost concern, then using a matrix is also not a bad idea. And you could think of why that would be. And the reason for that is this. So let's just kind of analyze our time complexity of our matrix, right? So analyze our time complexity. So to add something to our matrix, I mean, that's a scary one. I mean, I guess you could kind of extend this past for potential ads. So future, I guess you could say, like potential like nodes that you might want to add. So if you're kind of modifying your matrix, it's not like super costly. But if you were to modify a matrix, it's actually very costly. It's O of V squared, right? Because you have to not only copy all of the elements, um, you have to also reallocate all of those elements, right? So I have to reallocate this whole array and then one by one copy all the values into the new array, and then add obviously like more entries, right? You're going to have extra entries there. It's just kind of like a very expensive operation to actually add. So add with a matrix could end up being V squared. Obviously, you could kind of store extra places and then only have a certain number of nodes in here. And then if you're going to add, you could do it pretty easily. I will say this though, deleting is a almost nightmare. And I say that because, well, there's a few ways you could probably handle deleting. It's not something you want to do on a matrix, right? You don't want to have to delete a row and delete a column, right? Because if I get rid of, let's say I got rid of this entire section right here, right? You could just consider that as zeroing out all of these. That's probably the easiest way to do something like that. So O of V, um, that way it doesn't map to anything and nothing can map to it anymore. So you just kind of have this stale node, not doing anything. You're not really deleting anything, right? You're kind of just removing it from your graph almost. So removal. In this case, it would be O of V, right? 2V, just remove it, right? But you're not really deleting it. So this memory stays here and you're going to have this permeate in your data structure. So there are other ways to get rid of that problem, except they're a lot more expensive. Right now, you have to kind of remove this and then shift everything over, and it's going to become almost, I wouldn't say a nightmare, but it's not really fun, right? And obviously you wouldn't use a matrix for removal, right? So analyze matrix. That's kind of just the general consensus. But adding could be O of V squared. It could be O of, I would say O of 1, depending versus O of 1, depending on how you're keeping track of this matrix, right? Now, on an exam, is she going to ask you necessarily adding? Probably not. I think what she's going to ask is more of like relations, right? How do we add? How about like access, right? Access. And this is the big one. Access is O of 1. And what I mean by that is, well, like, does V have a connection to, does V1 have a connection to V3? Oh, that's O of 1 time. Why? Because I'm just kind of indexing this matrix as opposed to something like a list, right? A list is going to have a little bit different. But yeah, the reason why you would want to use a matrix is because of access, right? You're kind of doing a bunch of little tiny relation operations on your graph. So maybe you're adding relations, maybe you're removing relations. Now, removing a relation and removing a node are two different things. Removing a relation involves just going to an index, crossing it out, and putting a 0. Right? That's super easy. Compared to, right, because if this was VNV there, right, I'd be crossing these out, putting a 0. That's removal of a relation. Whereas removal of a node is a completely different operation. That's kind of important to keep track of. But also, anyways, when we're accessing these relations in a matrix, right, you could just go directly to their index and look like, well, okay, is that a 0 or is it a 1, right? If it's a 1, there's a connection. If it's a 0, there's no connection. There's nothing there. You can't access it. And these kind of ideas of like, well, how do you represent relations are kind of the main practices that you're gonna have to understand in order to kind of understand the main difference between a matrix and a list, right? Because we haven't even talked about a list, but definitely understand that a matrix, the representation of relations in the graph is a lot easier to use than anything that a list would use, right? So let's just kind of come up with like a simple example, and maybe do like BFS. Do we want to do BFS? Did you guys learn BFS yet? Let's do. Did you guys learn BFS yet? That sounds like kind of an expensive thing to do when we could just keep talking about lists, because I feel like lists are probably more important than doing BFS right now, especially if you haven't done. Have you all done BFS yet? Or is that something that she's like starting now? And this will count as participation. And maybe we could just come back to BFS and finish up the list. Okay, sweet. So I don't even have to worry about doing BFS with you today. Awesome. Okay, let me just extend this down. So let me just kind of look at her notes real quick, just because I haven't really. Let me see if there's anything specific that she kind of mentions about these before I go. Okay, so in adjacency matrix, she has adding a vertex is O of V squared. Yeah. We already covered that. Adding an edge, O of 1, right? That's kind of like the whole relation idea, right? Relations. So access, I'm going to say relations. Relations. is O, right? Because all of your relation operations, and that's kind of what you're using the graph for, right? Immediately when you see graph, you should understand that you're talking about relationships, right? This X right here, let's just kind of fill in random letters here. I'm going to put a J here. I'm going to put like a K here, right? The K is related to C and B. X is related to C, J, X, and B. K obviously has others which you can't see, but that's kind of the whole idea behind relations, right? I can access the relations on X through X. Or you could think of this as I could travel to other nodes based on their relations, right? If X is related to C, I could go to C, kind of like traversing a linked list, like current is equal to current.next, something along those lines. And you could kind of traverse this graph by just traveling along the relationships of the graph. That's a super important thing to see. And if you haven't saw that, I hope that kind of cleared things up, like why you even want to use a graph. Graphs are super information dense, especially in applications where you're storing them in kind of like this way, or you have some sort of really good hashing algorithm that kind of lets you have some sort of list that lets you go directly to the node that you're looking for. Maybe you start looking around it, right? Maybe you're trying to find like relationships around it. What's the general consensus of X? Well, it's all of these. And another way to think of this is, well, there's just so many. I guess one of the ones that, because I'm involved in a lot of robotics stuff. One of the ones that we do is we can kind of map out a grid like in a bunch of like squares down to like really small or really big sizes. So you could kind of split up any sort of area into like this grid-like fashion. And then doing something like that, you could figure out which grid that you're inside of, and then based on however much distance you traveled in a direction, you could find which cell you've traveled to, right? And then that's kind of like if you have any sort of like, I don't know, maybe there's like a TV right here. You could kind of use that information to say, oh, am I in, do I know if I'm in this position, right? Maybe there's like a cup of coffee here or something that you're trying to like pick up with whatever robot you have. This TV being next to the cup of coffee might tell you something about the cup of coffee. But let's say you're in C, like for some reason you're in this cell in your graph and you don't see this TV, well, then you're probably not actually in the cell. You've just kind of mistaked yourself to be in the cell. So then you're probably in one of these other cells. That's kind of one of the applications that I could think of off the top of my head. Another application of these graphs you could think of in terms of, well, what's Twitter? What is Twitter? And then I'll give a very simple explanation of Twitter. Twitter is you and all the people you follow, like I don't know, maybe like Tom Cruise. Maybe you follow USF Engineering, USF Engineering, USF Engineering. You follow, based on this arrow, USF Engineering, but they don't follow you. But maybe they follow Tom Cruise. And maybe, if they're lucky, Tom Cruise follows them as well. And you can kind of see that like this whole idea of a graph can be used to represent many different ideas. And if we extended this one more time, let's say there's a student A, student A, and maybe some information on their profile says that they also go to USF, and maybe some information on your profile says that you go to USF. Well, then, if you're a decent enough programmer, you can kind of see where I'm trying to go with this, with the fact that, okay, if you both follow USF engineering and you both go to the same school, well, then maybe you guys should be friends. And that's how recommendation algorithms come into play, because when you start to find relationships that don't actually, when you start to find relationships or similarities in nearby connections, you could kind of start that path into relating other objects together. So, like if you have book, and this is like an NLP, I guess you could say, application, right? Like, how do you know which words are related together? They appear near each other in the same graph, right? And you can kind of, I'm not even going to go into that one because that one's way too complicated to even continue, but this is kind of like the best one that I could kind of quickly off the top of my head give you as like a quick explanation of how, why as a computer scientist you would be interested in graphs. Obviously there's so many more. So definitely if you're going to pay attention to anything in this class, pay attention to graphs, because they don't ever go away. But in this case, right, like we could see how we could use this idea of having nodes that have these relationships, maybe storing other information, right? USF engineering is obviously USF school, right? If we all share this in common, then maybe if they follow them and we follow them, then we should follow each other, right? And this will get added to our like, you should go follow student A, right? And so on and so on. Okay, so let me just kind of move this out of the way because it's not really that important. I'll move this up here, but let's continue. So, like I said, relations really important. In all of these relation operations is like all the places where she says v is adjacent to u, removing an edge, right? That's kind of like a relation operation because we're unrelating two things, right? Relating, unrelating, two of the same piece. Adding an edge is O of 1. And obviously she has here O of v squared for adding a vertex and removing a vertex. In memory, obviously, O of v squared, that one's very intuition. You could, like I said, you could add and remove vertexes in a better way if you had to use this by keeping extra space. And you could remove, like I said, by just zeroing out the value from your graph. So it's literally unaccessible. Like you can't get there, not even from itself. And then in that case, you haven't removed it, but you've kind of like, I don't know, if you've ever like went online and found like somebody else's code and like copy and pasted it and kind of like changed the variable names, but like it still has errors, but at least it compiles. It's kind of like that. Like you haven't gotten rid of the problem, but you kind of put a bunch of things over it and kind of forgot that the problem was there in the first place. That's this. And that's kind of like an alternative to what her thing is. Not that she's going to test you on what I just said, but it's important to kind of see in the sense that understanding what I just was talking about, how you could extend this and kind of just forget about this. That's kind of like, well, critically evaluate what this representation is doing. Other than that, let's get into the lists because the list is probably the best way to represent a graph, in my opinion, only because, like I said, you could do a lot more with lists. You could hash lists. You could represent everything as kind of like a list, but have like a good way to kind of like find things in your list, right? So maybe you're sorting elements in like a binary tree or something like that, right? Because I mean, you could represent a list as a binary tree in an in-order traversal, right? So let's say you have some mechanism to sort your nodes, right? Then accessing nodes can be O of V, right? Because If you have a list that's V, so I'm just gonna say our list, our nodes is just O of V. Let's say O of V. Well, then actually accessing the nodes would be O of log V, which, like I said, is probably something you want if you're trying to access nodes often. Like I said, in this case, you're using up tons of memory. This uses V memory and and however much memory each node is times V, right? This uses V memory to store, and also you could find things really quickly because of the logarithmic property, right? So don't necessarily believe that this operation is O of V. Let's see what she has it as. Finding. Memory O of V times E, adjacency list O of V plus E, which I guess is right. So removing a vertex is O of E, removing an edge is O of V is adjacent to U is O of V. So I guess this V is adjacent to U is doing search. So it's searching through this. And like I said, if you have a very bad way to store your vertices, then obviously it's going to be O of V, right? If you're just storing vertice, 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 and this is V1, V2, V3, V4, all the way on, then actually finding a vertex in your graph is going to be, like I said, O of V. But I would also suggest that, because obviously these graphs aren't going to go away, for your future reference, outside of this class, understand that you could find a better scheme, this one right here, to represent your, I guess you could say, adjacency list. And that essentially is kind of, I guess you said, the takeaway from this piece, right? You're representing these nodes in a list, but like I said, a list is just a collection, and you could represent a collection in many ways. Anyways, moving on. So let's just kind of start talking about some of the operations that she has you guys doing. So let's assume that the memory that you have to use in order to store V is just some V, right? It's just some constant. And then I'm gonna that out. I'm just gonna say, well, like some constant. I'm gonna call it C. You have C times V. I guess you could say vertices for memory. Then, but then you have to have some sort of way to kind of draw these links in, right? And these links are actually super important, right? These are super crucial to your graph, right? Why would we have a graph without any links? It doesn't make sense. And you could see that for each link, we're going to have to store it in memory, right? Each link is going to take up K memory. So how many links are we going to have? She calls them edges. So I'll put E here. So we're going to have C number of vertices and K number of edges. So you could see that I should rephrase that. You're going to have V number of vertices that take up C memory, and you're also going to have E number of edges that take up K memory. So what do I mean by this? And I'm sorry to kind of drag this one on a little far. Your C and your K are constants, so they're going to cancel out because, like I said, any constant in an expression like this, we don't care about, right? That kind of goes back to the whole time in space complexity arguments, which means that the only things that can actually change are these V and this E, right? So we're going to kind of take this out, and we're going to say that our memory is in terms of O, V, plus E. Just like that. Now, I would even argue that there's other ways to represent something like this. in the sense that you could kind of come up with some constant number of E. So make E in terms of V, if that makes sense. So what I mean by that is in this grid expression, right? The number of vertices that you're going to have is 4, so some constant, times the number of vertices. So you're kind of changing this expression from O of V plus E to O of V plus 4V. So really just 5V. So this ends up just being O of V, right? Because you're having a fixed number of edges, right? Granted, that doesn't matter in this case, right? This is always going to be O of V, but I'm trying to give you an alternative perspective on something like this, right? Because if you're looking at this and you're telling me, well, why is this O of V plus E? Well, it's because I could do something like this if I really wanted to in a graph. That has to be allowed, right? Because it's a graph and I could relate nodes together. I could also do something like this. Granted, my graph in this case wasn't allowing that, right? This is what I call a grid. I don't think there's any necessarily like formal definition for something like this, but in this case specifically, you have only at most 4 connections, and that's a constant. That'll never change. So if I have at most 4, then that is going to be just in terms of V, right? Just for kind of like arguments sake, and kind of demonstrating how this is different. But where this kind of plays in more, this O of V plus E plays in more, is this Twitter, right? I could have infinite number of followers, and I could follow infinite number of people. I shouldn't say infinite. I should say I could follow a bunch of other people, and a bunch of other people can follow me. But I could also follow nobody, and nobody might follow me, right? I'm very lonely, very, very sad and by myself in this kind of corner. No connections for me. Break those off. And in that case, right, you're gonna have V as this memory piece right here in 0E. But then in the case that your E becomes super large, meaning a lot of nodes are incident on it, your E is going to start to play a higher factor. So depending on the number of connections in your graph, in this case, right, it's going to affect the memory required to store this graph, if that makes sense. So really what I'm trying to get at is, in a graph like this, where there's no external constraints, in this, like I said, external constraints, you wouldn't have a graph like a grid where you can go from here to there, unless you're playing like Pac-Man, and like going out one corner brings you to another corner, right? That's kind of like one example of like how you could kind of take this and convert it kind of into that. But in this case, it's kind of implied that you could just kind of follow off on many other people, many accounts. You could follow so many different accounts on Twitter, and create these little connections between you and the other account. But if you don't follow anybody, right, then that's not really going to affect the number of memory required to store your account. Now, what I'm trying to get at is, in this case, E is a free variable. E is free. And because E is free, we find that property. I guess that's the best way to describe this. In this case, like we said, E is not free, and therefore it doesn't really matter in this, right? This kind of boils down to O of V. In this constrained E, right, where E is constrained. But where E is not constrained, you're going to have to represent it in terms of whatever the space complexity is. Okay, moving on. So let's kind of take a look at some operations, right? In terms of, let's just kind of build out our graph in terms of our list. So this is V1, V2, V3, all the way onto Vn. And I like N. You guys will see N a lot in future classes. But let's just kind of come up with a graph where all of the nodes are connected. And we'll call this the fully connected graph. And you might ask, well, what is something like this used for? If you've ever taken a machine learning course, graphs are usually fully connected in there. So it's kind of synonymous to that, but anyways, are these ones connected? Yeah, these are connected. So assume all of my nodes are connected, right? We call this our worst case E. Fully connected. And we're going to try to perform some operations on this. Okay, so let's try to remove an edge between VI and VN, right? How do we do that? Well, VI VN. And then do the relation. So these two are connected, but we could just kind of like remove it. Hold on, let me fix that. I'm gonna remove it. And let me label this as well. So removal, edge, operation. So we have to look all the way in our list to find VI, which takes I number of operations. And same with VN. We have to look all the way into our list to find VN in order to perform this edge operation. This edge operation, we're actually removing the edge, is constant time, right? It's not really that big of an operation to just kind of like this connection is nothing and this connection is nothing, like just kind of removing the reference to each other. But the expensive operation here, you could see, is the search, right? Through our, I guess you could say, adjacency list, which for us, right, it's funny because, like I said before, you kind of represent it like this and get this better. But I digress. This whole search is what's costing the, I guess you could say, the amount, right? We have to find VI and we have to find VN in order to remove the edges, right? That's the big deal with this one. And if you could kind of like think about like, oh, how do you remove an edge? Find this one. Oh, we're doing V operations. Find VN. Oh, we're doing V operations. And then we're doing this removal. That's O of 1 operations. Because it's just a constant number of operations, O of 1. The majority of the work here is being done in the find, right? Find is O of V. Now let's kind of change pace and talk about vertex removal. Now, if I were a programmer and I wanted to kind of optimize this, right? I might start by, I guess you could say, if I was gonna, I know I spelled this wrong. If I was gonna remove a vertex, well, I might just try to find the vertex, right, and then remove it. But I think the most important piece of this is, well, if I give you a vertex, right? Given a vertex, given V1, remove it from my graph. Well, you have to understand what this is saying, right? I'm just going to say VI. Remove VI from the graph. If I want to remove this from the graph, well then, what is it connected to? Right? Is it connected to V2? It's connected to V1. And you could think of this in terms of, well, in this worst case where everything's connected to everything, it's going to be V, because V is equal to E. Or not V is equal to E. V is equal to, I guess you could say, V, E is equal to V squared. But, right, that's just kind of like in this example. I'm trying to think why I came up with this fully connected graph. Anyways, let's just say your worst case, right? E, I guess you could kind of assume E is like the max number of connections between any two nodes. So like what's the most highly incident node in your graph? What that means is, what's the node with the most incoming and outgoing connections? That's the one that's going to make this operation really expensive, right? So if this is VI, I'm going to say VJ, then I have to go through all E number of these edges and do this removal, right? So like we said, like each one of these nodes can have any number of connections to the others, right? That's kind of what we kind of came up with here. I have some number of connections. I have some number of followers. I have some number of following. And we're going to have to, if we delete our account, we have to go to each account that we're incident on and remove that reference, right? If I delete my account, Tom Cruise cannot have me as a ghost follower. It will never get removed if I don't do that. So if I'm going to remove my account from Twitter, I have to go to all of the accounts that reference me and remove those as well. And you could think of that as E, right? I have to go to E number of things, because in this case, right, I'm connected to every single node. Every single node's connected to me. I have maybe infinite number of connections into me, and everybody else is super sparse. So essentially a graph that kind of looks like this. And it's important to think in terms of like, what's the worst, I guess you could say, representation graph that I'd have to manage when we're dealing with worst case. It's this. I'm removing this guy, because I have to go to all of these connections and remove them. And there's no other connections in the graph except for this one. This is the root. This is like the connector. Everything's connected to me. In this case, I mean, I don't know. I'm trying to remember why I brought this one up. I feel like this is just kind of a special case. I'm not really sure. I think I had an idea of why I brought it up, but forget about this fully connected stuff. I know there's other operations that you could do that make this really annoying. So like this is a worst case for something I can't remember. But in this case, right, you are the connector to all of these other nodes, like V1, V2, V3, maybe V4, maybe VK, VJ, I mean, and we're deleting VI, right? That's this guy right here. And in this case, when you're deleting VI, I have to take off all of these, and there's E number of them, which means that in this graph, you're only ever going to have to delete at most E number of references, right? Because you're not getting rid of these nodes, you're getting rid of these references. And that's like the high bound on whatever this is, right? And as a computer scientist, just because like I remember when I learned this, I was like, what? Huh? You have to think in terms of like extremes in order to understand, oh, time complexity and oh, space complexity. And the extremes are this, right? You can have 1,000 of these nodes all connected to V, and it's gonna cause every single E to get removed because no matter how many things you have incident on it, I guess you could say is like the kind of time that you're going to have to spend doing this, right? This edge operation. Uh, the cool thing about this is we don't have to search for these because these edges should give us the direct reference to whatever node we have here, right? So you could think of that in terms of, well, if I'm at this edge, or if I'm at this node, I'm kind of like traveling to here, that should be an O of 1 operation. Same thing here. I should be able to travel to this node in O of 1 time, travel here in O of 1 time, travel here in O of 1 time, and travel here O of 1 time, and so on, right? Which is why we don't have to search for them. That's crucial. But when it comes to this, we have to get rid of at most E number of connections from a graph. All right, so it's 11:56. I'm just trying to think of anything else I could kind of go over today. We went over Twitter. We went over, I guess you could say, the little robotics application I was talking about. We went over adjacency matrices. We went over adjacency lists, and we kind of went over the main operations which separate them. Obviously, adding an edge to this to the list is O of 1. And you can see that because if I have a graph with a list, adding to the list, right? Like I said, I could just have a bunch of empty null spaces, maybe like 20 null spaces for a 15 node graph. Adding to that is just O of 1. Because adding to a list is O of 1. Adding an edge, also O of 1, right? I'm just kind of like, you are here and we're just kind of by linking nodes or whatever you would like to call it. Not really doing anything crazy. You're just kind of linking up things when you need to. And I'm trying to think if there's a connection between two nodes, right? You could kind of think of that as like, how do you actually find if there's a connection between two nodes, right? Let's say I have like a key for node 1. Let's say a key for V1. I'm gonna say so keys, some identifier, right? Maybe it's your profile name, maybe it's like something like that. And I have like V1, V1's key and V2's key. And I want to know if V1 is following V2. Well, I remember my friend in like freshman year, he did something like this for like an unfollow Instagram bot. So this would go and unfollow everybody who didn't follow you. So you can kind of think of this as if V is not adjacent to you. But anyways, if V is adjacent to, I guess you could say V2, so V1 and V2, if there's a link between them, right? Then I'm going to be able to find that. But first I have to find V in my graph. And then I have to find V2 in my graph. And then I have to compare, right? And this is like a naive way to do it, right? Obviously, there's better ways, right? I'm trying to get this point across. And this is why, I'll be honest with you, I wouldn't necessarily believe that this operation is O of V. Because it's not in some cases. Where finding V in V is easy, right? If I could instant access, let's say I have a perfect hashing algorithm that gives me V in O of 1 time, right? And this is the crucial piece to like what her thing is saying, right? V is incident to, because I have her documents up right here. This is kind of like, she doesn't really like slow removal for list search times, right? You're searching through a list. Well, that's assuming you're storing this in a list, right? Because like I said, binary search tree, um, have a way to compare strings. Obviously, the string comparison might be expensive, but if it means that you get to store like things like a lot better, right? You're sorting strings. Maybe that changes. Maybe if you have like a million like vertices, and you have like, I don't know, at most like 25 names, 25 characters per name, right? You could say, well, it'll take at most O log n, so O log v, O log v times, so times at most 25. So we have to do at most O log v comparisons and at most 25 comparisons with the string, right? So if I have a username, and this is why I don't like her slides for this. If I have a username, 25 characters, right? 25 chars. Then if I want to check if one string is like alphabetically less than the other, it's going to take at most 25 operations to do so, right? In that case, we have that here. We're putting a cap on the number of characters you could use to represent a username. Now, if I have a million nodes that I have to do this for, but at each index, we could kind of, let's add one more zero. If I have a million nodes that I have to do this for, right? Let's import math, math.log of, I think it's a million, one, right? You have to do at most 13 operations. That's a lot nicer than doing a million operations. And this 25 doesn't really do anything, right? You could see that. So if you have a good way to search your list, then you could kind of ignore her bad time complexities here, right? Is V adjacent to U? Is removing an edge, right? And this whole idea of finding a better way to store it, right? She's even mentioning it here, slow removal times for list search times. That whole idea is stemmed in the idea that you're using a list to search in a naive way. You're not using any other properties of the data structure in order to perform the search. So if you are performing search often in your data structure for a graph, and you have a way to do better than O of V or O of N search time for whatever you're trying to look for, like I kind of proposed here, then this will always be better than these, right? Because you could add and you could kind of remove in terms like this removal, right? This is a very extreme case, right? This is at most O of E, and it's very rare that it is O of E. Um, and this memory is obviously better than all of these. Um, and this removal and this adjacency, right? This whole idea stemming from here. And if, like I said, you could beat the naive search, then this will almost always be like O of log V, O of log something, right? You're going to have logarithmic properties here, which will always, always, always be better than these. That's if I could give you like one piece. Um, Obviously, for exams, stick with these because assume naive, and assume that that's kind of like the upper bound for your naive based graph. But like I said, in practice, you're never going to use a naive based way to do this, and you'll almost always use something like this, where your keys are hashable. Your keys are, I guess you could say, your keys allow access to a different structure. Um, and yeah, like a username. It's a unique identifier. You can't have two users with the same username. I could sort my entire graph based on a username. And then my friends, you get very nice behavior. Yeah, that's really all I have. I don't think I have anything else. Obviously, if you have any questions, let me see. Is there any chat questions? Is there any questions before we call it a day? Let me just create a new poll. And even if you don't have a question, respond to this poll, because if you haven't been recorded for attendance, it will record you for attendance. Yeah, I'll be honest with all of you. Things like this, obviously, like aren't going to get you extra credit on the exam, I don't think. But I think it's more important to understand this for A, future classes, but also B, like if you ever work at a job and you get O log V search through your graph. Test 3 was actually pretty easy. Test 3, we're gonna work. I remember test 3 really well. Test 3 was actually probably the easiest one. I got like perfect score on it when I took it. I know it was like the highest performing exam. I think the average was an 87. So is there really any coding on it? Yeah, you have to code breadth first search and depth first search, which we'll talk about at another point. But you're not doing any of this. You're answering questions about this. So definitely know this. This is really important for test. I'm trying to think. This whole thing is really important for test 3. If you memorize this, like I said, then like yeah, you'll do okay. Memorize this and understand how to program. We'll walk through all the things that you'll need to program on test 3. Or maybe we'll need to program on test 3. Can't really say for sure what she's gonna put on there. I don't know. I'm not TA that grades, so I don't actually handle any of the exam grades. I handle some of the project grading. But even then, I'm just kind of running all of your projects through like a grading algorithm, and it does it all for me. So when it comes down to grades, I'm not the best person to ask. Definitely reach out to, I think it's Joshua. I think Joshua's the one who's doing all the grades. So I think Joshua is even, I don't know if you guys use Discord, but if you do, Joshua's pretty active, I think, in the USFCS Discord. So if you haven't found his Discord yet, we'd always reach out to him. I know he's really nice dude. So definitely, I'm trying to think, can I find Joshua in here? Yeah, but yeah. Yeah, so if you're doing well enough, and I'm gonna stop the recording here. If you're doing well enough in her course, up to this point, meaning like you have like an 80, an 85, you probably won't need to take the final. And I say that because I had an 85 in her course up to this point. And when I took test 3, I didn't have to take anything else because extra credit was really nice. It was 10 points, plus the exam questions were pretty easy. So you should be able to get perfect score on this one. And obviously the previous exams were kind of more challenging in the sense that you guys aren't exposed to this stuff, but you have to realize that a lot of this stuff is building on top of each other, right? Hold on, did I stop recording? I'm gonna stop recording. A lot of this stuff is building on top of each other.